Yes, am I audible? Hello. Hello, am I audible? Yes, am I audible? Hello.
Yes, sir, you are audible, sir.
Yes, and the screen is visible, right?
Yes, yes.
Okay, okay. So in the first part of the session, we'll just see some simulations and try to apprehend the results, right? I hope the screen is visible and my voice is also audible, right?
Yes, yes.
So what we are trying to see here is we have a AC supply and we have the diode bridge rectifier. It is a single phase. I have emulated it as a 3-phase, but it is just emulating a single phase supply. As you can see, I have connected one line and the ground. And this is a 2-arm, that is 2-leg, and we have 4 diodes. So it is basically a single phase diode bridge rectifier connected to RC load, right? So this is what kind of load? Can any one of you tell me? If C's value of capacitance is very less compared to R, then it can be considered as a linear load, right? For example, if you see, if I make the value of C quite small compared to R, for example, R is taken as 10 ohms and resistance is much larger compared to the capacitive admittance, because if you reduce the value of the capacitor, then the capacitive admittance will be much higher. So effectively, it is just a diode bridge rectifier connected to a basically R load. Okay. So if I simulate it, as I told you, the meaning of linear loads, the load voltage and load current at the AC side should be it should be proportional, right? So as you can see my screen also, if I open, you can see the load voltage and load current, first two. Okay, the first one is the voltage, that is single phase supply that we are giving, and then we have the input side current, AC current drawn by the diode bridge rectifier, and this is the voltage and this is the current at the DC side, right? Output voltage and output current. So you see that the load voltage and load current are proportional, and they are also linear, right? Because obviously the definition of linear does not have any relation with sinusoidal nature, but since the supply is sinusoidal, the load current is also sinusoidal, but the load is linear. Now if I ask you what is the input side power factor, what can you say? The input side power factor should be, so someone was having doubt in the previous week also that IS1 and IS8, right? And IS1A, that is the active component of the fundamental, and the harmonic. So these concepts are very important. So to make you understand, I just thought we should have a discussion on this. So if you see, what can you comment about the input side power factor? Seeing these two waveforms of the voltage and current, what is the definition of, I can say, displacement power factor? So do you see any overlap? Since it is sinusoidal in nature, the voltage and current both are sinusoidal in nature, no question of distortion factor. Okay. So power factor comprises of two terms, distortion factor and displacement power factor. Now, since we are talking about sinusoidal waveforms, our distortion factor is unity. Okay. So what can you comment about the displacement power factor? It is, do you see any phase shift between input voltage and current? No. They are in line, right? So they are in line means that the power factor is unity.
Yes.
So now let me increase the value of capacitance, right? Let me make it 100. Now see what changes we see, okay? Do you see any change?
Yes.
What is the change?
Distortion is there.
Correct. That is the first observation. And what is the second observation?
Second observation is that they are in phase, I think, but
Do you see
distortion is
the
there.
crest of the sign? Just see the crest. Do they coincide? That is, do they appear at the same time instance, or there is some shift between the two signs?
Yes, yes.
There is some shift.
There is.
If you see carefully, then the current waveform is distorted, agreed, and also the current waveform, that is of the input current I am telling, is slightly leading in nature, right? It is appearing before the voltage, the crest. So what can you comment about the power factor? The power factor, as I told, I am repeating also, is comprised of two terms. One is the distortion factor, another is the displacement power factor. Displacement power factor is related to the phase shift between the fundamentals of the two, that is the voltages and currents. And the distortion factor is the measure of the content of harmonic content of the signal. Okay. Now the current signal is already distorted, so means that its distortion factor will be less than 1 because it has some harmonic content in it. Apart from that, we also have a shift, that is, it is somewhat leading the voltage current, that is current waveform is leading the voltage. So what can you comment about the power factor?
Power factor is leading.
Leading. Now why power factor is leading, do you think? Can you?
Because there is capacitor current is reaching a peak before the voltage.
Yeah, current. Yes, correct. But why do you think there should be leading power? That is power factor. You cannot see the. That is, if you see the DC wave, DC, that is output current. Okay, the output current. If you see, let me increase the capacitor value more. Then you will understand. Okay, let me make it 1000. See, now the crest is appearing more before the voltage crest. Okay, so more leading. So why this is happening? If you see carefully, then it can be apprehended to the difference in charging and discharging of the capacitor, the difference in time constant. Do you see the charging? See the charging time and discharging time. Charging time is more or less instantaneous. As you go on increasing the value of the capacitor, it will charge immediately because the diode paths during the conduction of the diode pairs, the impedance offered in the charging path is very less. However, when you discharge the capacitor, the capacitor means who are involved in the discharging path? Only the R and C, right? Because then no diodes are conducting. Do you get my point? What I'm telling is that let's see one cycle, okay? So what is happening? This is one cycle, okay? This is full cycle. So between that, two instances are happening. Just see 0 to 180 degree. For example, consider on one sine cycle. So this is one full sine cycle, and this is the positive cycle. Okay, just split it in two halves. In this, during the positive half cycle, you observe one charging instance and one discharging instance, right? Hello, am I audible? Hello.
Yes, sir. You are audible.
Yes, so what I am saying is that just consider on one sine cycle. And during one sine cycle, just focus on 0 to 180-degree time period, any one of the positive or negative cycles, okay? Then you see two instances, that is during charging, when will the capacitor charge? Because capacitor has some initial voltage across it. So it will just keep the diodes reverse bias till the supply voltage exceeds its threshold. Hope you understand that. So just assume a midway situation, okay? That capacitor already has some charge, that is V0, average voltage across it, and when the supply voltage will exceed that, then only the diodes will be forward biased. When what I am telling, when the diodes are forward biased, you can see the charging of the capacitor, that is voltage, output voltage rises. During that time, the time constant is different, and during the discharge path, since the only the RC circuits are involved, because no diode is conducting at that time, then it is longer due to the larger value of the resistance, okay? R is more, right? We considered at the beginning. So that's why what is happening, this waveform, again I am zooming. Yes, this waveform is not in line with the sine, right? There is some non-linearity, and that is where the non-linearity is also reflecting in the input currents. So this is the main reason, the difference in time constant of the charging and discharging path of the capacitor is leading to the shift in this waveform. Because in DC you cannot tell that since capacitor is connected it will be leading power factor. So that flavor does not appear here. So the main reason is that due to the shift in time constant of the difference in time constant of the charging and discharging paths during one cycle, that is positive cycle or negative cycle of a full sine wave, you experience that is difference in time constants. That's why this crest is appearing not in line with the sine. If you increase the capacitance value, you will also see that. So that's why if you find the fundamental component of this input current, it will be leading in nature. So distortion factor is also not unity, and also displacement power factor is leading in nature. That's why when if in the exam someone asks you that you have some RC loads connected to a diode bridge rectifier and what is the power factor, then don't tell it is unity, okay? It is not unity power factor, because if the capacitor value is somewhat more, then you will experience somewhat leading power factor. So it is possible that a single phase diode bridge rectifier is drawing leading power factor, okay? So that's what I was just thinking too. But if it is only single phase diode bridge rectifier connected with R load, then your power factor is unity as well as distortion factor is unity, just as I showed you, right? You see here, voltage and currents are also sinusoidal and no phase shift. So this concept is very important, right? And don't confuse between the active and reactive component. The active and reactive component only happens when the waveforms are, we are talking about the fundamental component of the waveforms. Only then active and reactive power terms will come. Because if voltage don't have any harmonics, as you see, then the current fundamental will only contribute to the active and reactive power. So first you determine what are the steps. First you determine the fundamental component of the current, and then you see how much is the phase shift. From that you can apprehend what is the phase shift means in terms of angle. Then cos of that angle of the fundamental will give you active component of fundamental, that is active component of the current, and sine of that angle will give you reactive component of the current. Hope this is clear, right? Because
Sir,
we'll do.
but if the power factor is not given, sir?
Yes, that's what I'm telling you. If the power factor is not unity, then question what is it making it not to be unity? Is it because of the distortion, or is it because of the phase shift? Please understand. If there is phase shift in the waveforms, if you then decompose into their fundamental components, there will be some phase lag or phase shift, right? So cos of that phase shift will give you active component, and sine of that phase shift will give you reactive component. Then also power factor is not unity. But power factor can also be non-unity during the existence of distortion in the waveforms. Do you understand that? Even if the waveforms, just let me show you one simulation, you will understand. It is possible that power factor is non-unity even if the waveforms are completely aligned. Just see this example. Make it 3-leg and that is 3-phase diode bridge rectifier. Just see this example, okay? So now what you have? You have a 3-phase diode bridge rectifier connected to R load, right? So what do you think? This load will be linear or non-linear or power factor unity, non-unity? What comments can you give about it? We have solved many such problems.
Linear as well as unity power factor.
No, it will be non-linear. Just see. Why I will make you understand. Just let me simulate, okay? Your concept will be clear now. So do you see any distortion in the waveforms?
Yes.
But you don't see any phase shift of the crest. Please understand. So if two waveforms of voltage and current are not having any phase shift, then their displacement power factor is 1. What is the meaning of displacement power factor? Displacement power factor means the shift of the fundamental of the waveforms. If you decompose this current waveform, which is now distorted due to the quasi nature, I told you also that 3-phase diode bridge rectifier, since it does not contain third harmonics, will have quasi nature. You must have seen many problems. So that current, if you decompose into sine, its crest will align with the crest of the voltage, for which there will be no shift. Since there is no shift between the fundamental of the current waveform and the fundamental of the voltage waveform, we can tell that the displacement power factor is unity. That means it is completely. Can you comment about power factor then? It is not unity because power factor, I told you, is the product of displacement power factor and distortion factor. Since the waveform is somewhat distorted, then your distortion factor is not unity. Do you understand that? Hello?
Yes, sir.
So since the waveform is distorted, you cannot comment that the power factor will be unity. Okay? Just let me. So that what I am telling is that since the waveform is distorted, the power factor should not be unity. And why is it distorted? Because it is a 3-phase waveform. Okay, so it cannot contain the third harmonic components. So that's why it is quasi nature. 60 degree, 60 degree, it will be 0, and then it has some path in the 180-degree cycle. It will be conducting the remaining times. Okay, so that's why you that 60-degree no conduct that is it should not have any current component, and then the remaining 120-degree it will have this kind of distorted waveform. So that's why you can expect a non-unity power factor. However, the current, as you understand, is purely having active component, fundamental I am telling. But there are also harmonic components for which you don't get unity power factor. So don't confuse between power factor, distortion factor and displacement power factor. If you are confused, just go back to the week 1 and see the lecture. Or you can also visit the course and just see the first module where you have been given some examples and also some problems on those power factors and all those things. So this concept is very useful. Now, when we will be solving the problems also today, you will see that many such instances will come. You should not be confused, right? So seeing this waveform, one thing is clear that it is not drawing any reactive component, because reactive comes of the fundamental of the two shift between the fundamental components of the voltage and current. Now, since there is no shift, 0-degree shift, then sine of that angle will be 0. So no reactive power, right? So that's what I wanted to make clear through this simulation, right? Any other doubt you have regarding power factor, you can just ask now. I can just explain. Power factor and harmonic components, all those things. If you have doubt, just ask. We'll also solve problems. It will give clarity. Yes, if there is doubt, you please ask. Please feel free to ask, okay? Because this is important. If you don't understand this, you will make mistakes in all the problems that we will be solving today also, right? Is there doubt?
Sir, yes, there is a doubt, sir.
Yes, please ask. Please ask.
Sir, in one problem, the RMS current rating of active power filter is asked only for reactive compensation and harmonic compensation.
Correct.
So, which one will be the current rating for the reactive power, and which
That's
one
what I
will be
am
the for
telling.
harmonic?
It depends. It depends on the design engineer who is designing. For example, you are solving the problem and I give you some problem stating that you have to design some power filters. Now, I should also give you the targets that for what you should design the power filter. You understand that, right? For example, I tell you only my load current has so many harmonics, but my filter, you design the filter to only compensate the dominant harmonics. For example, my load is fully distorted containing maximum fifth harmonics, right? So I tell you to design a cheap filter which has only fifth harmonic compensation, no other elements. So you will design according to that, such that your such that your filter provides a low impedance path to my fifth harmonic. Now, if I tell you design for fifth and other higher order harmonics, you design a fifth sub branch and a high pass filter branch. And if I tell you, okay, my load is completely linear, but there is some reactive components. So then you should also compensate for the reactive components. So there are no question of harmonics. So then your current rating will change depending on how much reactive currents you need to handle, such that you can compensate for the reactive current of the load. So every problem to problem, what are the targets? You need to see first that. Then the targets will set the design constraints from where you will just write the equations to find out the filter current rating. The current rating will come from the constraints only. So if the question asks that find the filter RMS current rating, assuming that your filter is designed for harmonic compensation, then only you have to do. You have to find the harmonic current, reactive current component of the load. That is the reactive demand of the load, that current peak amplitude, and then that will be set as the rating of the filter such that it compensates. You just design an appropriate capacitor such that it only pushes the reactive component of the load, such that your supply is not burdened with the load reactive power. So obviously in that case your current rating will change depending on the load power factor, how much load power factor you are connecting, and worst case condition you design that, the rating. Always for the rating you take the worst case condition. But if I now tell you the load has changed, the harmonics nature of the load current has changed, and accordingly your targets has also changed, then you're similarly for the harmonic components you will just provide the path, low impedance path for those currents, those harmonic currents, and their amplitudes may also vary. So then the amplitude of the filter current will also vary. Then the rating of the filter current will also vary. You understand my point, right? So every problem to problem, based on the load and the design constraints, these two guidelines will set the rating of the filter. Just we'll solve some problems also today. You will just see how, based on the targets, the all the values will change. Nothing will be remaining constant based on the guideline constraints, design constraints, and the functionalities that you want to achieve. Like example, harmonic compensation, they tell you. Then what harmonics are you compensating for? For that, you have to accordingly design the rating, because only those harmonics will find the low impedance path and will flow. Others will appear in the line of the supply. So your filter does not have to take those currents, harmonic currents. You understand my point? Yes, hello?
Yes, sir.
Yes, so every
Yes, yes, sir.
problem you will be given some different targets. Not all problems will have same targets. And also different problems will have different kinds of loads. The nature of loads will differ. So accordingly, your filter ratings will also vary because you want some different functionality out of some different loads. So you have to read the problem very carefully. Just see the problems that we solve. You will understand how every problem you have some different targets, different filter designs you have to make, and accordingly your filter ratings will change. So that's what the problem is designed for. and you need to follow the. Just remember one thing, that for shunt filter design, you just have to provide low impedance path to the harmonics that you are providing, that you are designing that branch for, just as we discussed in the previous session, and just ensure that the quality factor targets are also met. Accordingly, you will get the value of R, L, and C. Now check if they are providing reactive compensation, then your C value will be set. As you know how we set the C values for the 3 branches, if it is a 3-phase 3-wire system or a single phase system, then your C value will be designed. From the C value you calculate R value, L value, and from after you get L value, then you just calculate the value of R from the quality factor. So likewise you need to do, and also check what type of filters are you connecting. Check whether it is high pass tuned filter, high pass or single tuned filter. You need to know the circuits. Otherwise, although quality factor and all those things will be given, but you need to know at least how they look. From that you can just calculate one by one. First, if they don't want reactive power compensation, then you just calculate for the harmonic components, and then you proceed with the quality factor to find the value of resistors. So that is how you should do it. So any problem with the simulation, I can just explain again, or else we'll just move with some problems that will clear your doubts. I have selected such problems that will clear your doubts. Okay, so don't worry, you will be able to solve all the problems. So likewise, I have selected the problems, and we don't have much variance remaining, so you will understand easily and you can go ahead with the solving. So, but understanding this concept is very important. The power factor, the displacement, distortion, power factor differences, the harmonic and difference between harmonics and reactive power. The questions you are asking, like the reactive power compensation, harmonic compensation, all the concepts come from here. That what are the targets you want to achieve? Where in the place where you don't need reactive power compensation, like in this problem, this model you are seeing, na? Here you don't need any reactive power compensation. Why? Can you tell me? Any one of you can tell me just by unmuting yourself. Do you need reactive power compensation in this problem? Just see how the sine waves look. Let me show you multiple cycles. Do you need reactive power compensation design incorporated in your filters for this kind of loads? If I give you this load, yes, can you unmute? Any one of you can unmute. Just have an interactive session such that we can clear the doubts. Otherwise, the problem solving will be very difficult. You have to mug up. You cannot understand what is happening. Yes, any one of you can unmute and tell. Okay. Do you need reactive compensation for these kind of loads? Is the question. Hello. Yes, hello. Am I audible? Hello. Yes, my voice is audible. Hello. If I am audible, just one of you just tell me.
Yes, sir. Yes, sir. You are audible.
Yes, then answer what you think about that. Do you need reactive power compensation for these kind of loads?
So, yes, sir. You take a reactive power as well as harmonic compensation, sir.
No. This load I told you, na, that does not have any shift between the fundamental of the two
Yes.
current volts. Then if there is no shift, where is the reactive power coming from? What is the definition of reactive power? The definition of reactive power is the shift between the fundamental of the two waveforms, voltage and current. If there is no shift in the fundamental, then sine of theta is 0. Then where from are you getting reactive power? No reactive power compensation is needed. Only harmonic compensation is required. Now, if you are a design engineer,
so in that case, current will be 0, sir. Current rating.
Which current?
For providing reactive power compensation.
Reactive component of current is 0, not harmonic component. Please understand.
Yes.
There are harmonics. So if you want to provide harmonic compensation, which you will do for these kind of loads, such that your supply side don't have any harmonic, then your current rating of the filter will not be 0, because your filter will provide low impedance path to the harmonic components. Okay.
Yes.
Then how can it be 0? Only the reactive component of your current is 0. That's why you don't need reactive power compensation. That's what I am telling. Does not necessarily mean that the filter will not handle any current. The filter will handle the harmonic component of the current. But for that harmonic component of the current, there will be no active power transfer. Since why do you, can you tell? For the harmonic component of currents, there will be no active power consumed or transferred. Because I told you this, why it is so. Since the voltage is fundamental and currents are other harmonics, then the average power consumed for the harmonic components, if you integrate sine omega t and sine phi omega t, you will find 0. That's why we tell that I continuously repeat this statement that there is no active power transfer for harmonic components of the currents, considering voltage is fundamental or voltage is not having any distortion. I told you in the group also, right? This. The active power transfer for the harmonic components will be 0, considering voltage does not have any harmonic components. However, reactive component is also 0 since there is no phase shift. So only there are harmonic components of the currents which the filter needs to handle. So obviously filter current will contain the harmonic current of the load, ILH, right? We denote it by ILH. IL harmonics. That is the filter current rating. That we also calculated in the previous session. But in this session also I will just show you ISH, ILH and that active and reactive components, all those things. But please just understand this, and this is a very basic concept and you need to get a feel of it. Otherwise you cannot find the answers to the problems what they are asking you. Okay. Any doubt in this? Just ask me this point. If you are facing any doubt, just let me know. Any one of you. Yes, you can just unmute any one of you. If you have any problem understanding the active power, reactive power, distortion factor, displacement power factor, and your that load harmonic component compensation or reactive power compensation, you just ask, okay? Otherwise, you will not get it clear. Otherwise, you just see the first module of the course, okay? It is very well explained. You can just see there. Or else you can also just ask here such that we can clarify. Yes. Any doubt? Just feel free to ask, because this is an interactive session. Okay, I don't want to be one-sided. Okay. No one of you are unmuting and telling anything, so I cannot understand. Yes, hello. Any questions? Otherwise, I will move on to the problems. Or you want to see some simulation? Just let me know. You want to see more simulations, or just want to move to the problems?
Yes, sir. We will move to the problem, sir.
Okay. Then you don't have any doubt in this?
No, sir, because we don't have the MATLAB software with us.
No problem. You just see the waveform. I will give this waveform to you in the slides also. Okay. The slides that I am uploading every week, all the content that I am covering is included in the slides, as well as you can ask this code or whatever is explained during the session from me in the group also, so that you can just see it. Okay. I can provide you this file. Okay. If you need.
Okay.
So I think we can move on to the problems, and later on we'll show more simulations, right? Some control and those microgrids and those inverter simulations. Whatever you are solving, you need to also see practically, right? So that's why I thought. So now let me move on to the simulation. The problem solving, right? So let me present my screen. Is the screen visible?
Yes, sir.
Okay. Just let me 1 second see. So you can see the slides moving, right? Just let me know if there is any latency.
Yes, sir.
So the slides are moving. Okay. So first of all, I want to ask if any doubts are there from the previous week numericals, or someone was asking something that harmonic component calculation. So one thing I want to tell you, whenever you are calculating for any filter current ratings, you need to calculate it for the worst possible scenario. Do you understand that? So first point, whenever you calculate any filter ratings, we ask you to calculate any filter ratings, do it for worst possible scenario. What do you mean by worst possible scenario is that the situation for which the filter current will be maximum. Because if you don't design the filter for that point, or that I can say condition, then what will happen is that your filter design current rating will be violated. And during that condition, your operation will fail. Do you understand that? So when in the previous week we were designing, we did all calculation for the worst possible, that is lowest possible harmonic. Because for other harmonic components, the filter current that the harmonic current for those higher order harmonics will be quite low, as you understand. The dominant harmonic component is the lowest harmonic that you are designing for a high pass filter, that situation. So all the other higher order harmonics will be quite low, their amplitudes. So you design for the worst possible scenario. That is, for that problem, it was the 11th harmonic for previous week's problem. So why 11th harmonics? Because for that harmonics, the filter will handle the maximum amount of current. So we consider that for the design. Any doubt from that? Someone was telling me. So you compute all the reactances for the 11th harmonic, or whatever is the lowest order harmonic given. Clear? So this week what I designed is more numericals on the series power filter, series active power filters, and you have also the UPSCs, right? So just read this first problem. The single phase series. So it is a single phase system, series active power filter. And series active power filter, what you are using it for is important, is used to filter the voltage harmonics. So voltage harmonics, why they are appearing? They are appearing from the presence due to other loads and source impedance. So you understand that if the source has some impedance and your load is non-linear, then the voltage harmonics will also appear at the point of common coupling. That point should be clear. And what will the series filter do? Series active power filter, it will inject that harmonics such that your source side you can experience lower PhDs in the currents, because it is injecting those harmonics to the loads, and it will make the system currents, that is the supply currents from before. What is the single line diagram? Single line diagram is that you have source impedance, after that you have the device sitting here, and after this your loads are connected. So I can name this as load bus. Your loads are connected. So what I am telling, this filter is injecting all the harmonics required by the loads at this point. But before this point, your voltage was sinusoidal. So since this voltage was sinusoidal, this voltage was sinusoidal, the current will also be sinusoidal. Sorry, the voltage will also be sinusoidal at this point, right? Current is anyway the series combination, right? But its effect will be minimized, right? So this is the supply, and you have this source impedance. I can name it as ZS. So what are the harmonic components? There are the third, fifth, seventh harmonics. Okay. This situation is before the connection of the filter. So before it is connected to a critical load. The critical load draws 4 kilowatt power. It is given at 0.8 lagging power factor. Okay. So voltage harmonic components are already provided to you. So, and what it is asked, the RMS voltage rating of the filter and volt ampere rating of the active power filter. So how will you calculate the filter voltage rating? What I told you, the filter will inject all the harmonic components at this point.
Sir, I have a question.
Yes, please ask.
Sir, this series active power filter is used to filter voltage harmonic, no, sir?
Correct. Correct.
And shunt is used for current harmonic.
I will clear this. What is happening? You are using series active power filter. Okay. So you understand that actually both series and shunt are required. If you go to UPSCs, you will see both series and shunt are actually required at the time when you have source impedance. Do you know why? Because if the loads are nonlinear in nature, they will destroy the power quality of both the in terms of voltage and current. Why? Because if the load is having harmonics, then you understand Vs is purely sinusoidal minus IL into Zs. This is the VPCC. This voltage VPCC, and since this is distorted, this VPCC will also be distorted without the filter. I am telling. So VPCC also got distorted, and since VPCC got distorted, my load current was already distorted. So the power quality of the system, because this current will mitigate to this path, the power quality got destroyed. Now, what I can do in that point? I want to improve the current quality as well as the voltage quality. So will my shunt filter be able to improve the voltage quality? If the source is having impedance, this one, ZS. Will the shunt filter connected at this point to the load be able to improve the voltage quality, which is destroyed due to the nonlinear loads itself and the presence of the source impedance? Just answer this question.
No, sir. No, sir.
Shunt filter cannot do anything. Shunt filter can improve current quality at the supply side, as we discussed in so many problems. But as you also know, the voltage quality needs to be improved in terms of, that is at the point of the supply. that should not get distorted, as well as the current quality should be improved. So what we can do, we can inject all those harmonic voltage components in the VPCC by this device, which is termed as the series active power filter. Once you do that, your voltage at this point will be what? This point. Answer will be sinusoidal. Agreed or not? Yes, hello. Agreed or not?
Yes, sir.
Yes. Then what will happen if this voltage is more or less sinusoidal? I am not telling exactly sinusoidal, but close to sinusoidal. And this voltage is also purely sinusoidal because of the supply. Your current quality also gets improved. I'm talking about the supply side, right? Load will anyway draw its harmonic components. But that effect which was previously appearing in the supply side was more. So we connected this device to controllably inject the harmonic voltages to improve the voltage quality at the supply side. And thereby improving the voltage quality, we also improve the current quality at the supply side without disturbing the operation of the load. So that's what is the basic operation. Actually, nothing is like that thing that you have to use series, you have to use shunt. So there is no hard and fast rule. Everything depends on what you want. So voltage series that is filters have this property that you can controllably inject some harmonic voltages. Once you do that, your voltage does not that is your voltage does not needs to be necessarily distorted before the load point, because you are in either way injecting that harmonic component required by the load. So that's why the power quality can be, that is the voltage quality can be improved. And current quality is improved by the shunt filter. But here in this problem, it is not a concern, because don't consider these problems as everything will be, power quality will be 100% pure or improved, because the problem is designed to for you to solve. There is no shunt filter, so you must have a question in your mind: where will the load harmonics go? Load harmonics will not go anywhere. Load harmonics cannot be compensated in this case, but your filter can provide harmonic voltages, inject harmonic voltages to more or less mitigate the effect of those non-linearities in the current. They can reduce, but not 100% they can be reduced. Okay, that is the main thing. So we are talking about voltage quality, okay, not current quality in this problem. Please understand. You get my point?
Yes, sir. Yes, sir.
Yes. So voltage quality we are talking about. So just the problem simply asks you to calculate the RMS voltage rating of the filter as well as the volt ampere rating of the active power filter, simply in this condition. So what are the voltages that are handled by the filter? You need to understand. It is VS3, VS5, and what? VS7. And what are their contents? If you understand, VS3 is 13% fundamental. What is fundamental? VS1. VS5 is 8% VS1, and VS7 is 5% of VS1, as it is given in the problem. So can you compute what it is coming? It is single phase, right? And all are RMS. So don't get confused. These are all RMS. This is also RMS. 230 volt. Supply is not distorted. So it is only the fundamental we are talking about. So what is VS3? Compute and tell me.
29.9.
Which one? First one.
First one.
And then 5 and 7 also you calculate.
18.4. 5.
And VS7 is coming 11.5, right?
Yes.
So now can you calculate what is the filter that rating, voltage rating it can handle? Because you know that it has to only handle these three harmonics and their contents are also given. So now it is easy to calculate the VF RMS. What is VF RMS?
29.9.
No, what is 29.9? VF RMS. VF RMS is what? Filter voltage RMS. Filter voltage is third harmonics this much, fifth harmonics this much, and seventh harmonics this much. So the overall RMS is the square and then root over. Square sum then root over. You know the overall RMS we are asking. So what is this you calculate?
$36.96.
Correct? So this is the rating. Now, can you tell me after connecting this filter, this series active power filter, at which point it is improving the voltage quality? In this single line diagram. We are talking about improvement of voltage quality, right? Our main aim is to improve the voltage quality, which was distorted due to the source impedance and non-linear nature of the load. Now, my question is which point? Voltage quality at which point? Load point or supply point?
Before the point of common coupling.
Means that this point, right? Before the load,
Yes,
that is the point of common coupling we are talking. This point.
yes.
Because this voltage, if you see, will be distorted. This voltage. Why distorted? Because load current is still non-linear. But this distorted voltage, if are absorbed within this filter, then this voltage can be sinusoidal. So before filter, some different scenario was there. After correcting filter, you have some different scenario. Because this filter can controllably inject the opposite of the, I can tell, harmonic voltages, such that you can make it sinusoidal. So we are always, whenever we are talking about improving the voltage quality by connecting some series power filter, we are talking at the point of where the load is connected, because loads always need sinusoidal voltages. Sensitive AC loads need sinusoidal voltages, because if you connect some machines like 3-phase induction machine or even single phase machine, induction machines, there will be humming noise if you don't have sinusoidal voltages, right? You have rotational losses and heating, unwanted heating due to those harmonic components, along with the nonlinear loads. So this, to not disturb the operation of those connected loads, 3-phase loads, rotating loads, or single phase rotating loads, mostly the rotating loads, to not disturb their operation due to the connected other auxiliary local nonlinear loads, we use the series active power filter. So mainly the aim is to improve the voltage quality in those problems or in those kind of scenarios. But current quality is also important, because you will be paying penalty if you don't maintain or if you don't draw purely sinusoidal or somewhat sinusoidal, less than 5% THD currents you need to actually draw from the grid. So you have to make your arrangements to provide currents, necessary currents, non-linear currents to the load, as well as not disturb the waveform of the currents that you are drawing from the grid. So in that case, you need shunt devices. But in this problem, you don't need shunt devices, because problem is not telling you to do so. You need to only do calculation and you have done so. Okay. So accordingly, can you tell me what is the VA rating of the active power filter? Just see the load is linear load. Okay. In this problem, load is linear. The voltage had some harmonics due to some reason. So can you just tell me what is the VA rating of the active power filter? So what is the current? Line current, I can tell, or load current. Just see the single line diagram, it will be clear. So what is the load current? Can you calculate? So it is 4 kilowatts and it is single phase. So what is the line current? 4000 divided by, calculate you, 230 into 0.8. Single phase, right? So what is the RMS of the load current or line current, whatever it is?
21.7.
Yes, 21.7 amps. Okay, 21.74 amps. It's coming. in amps, okay? Because it is 0.8 power factor lagging, it is given already. So now can you tell me what is the current handled by the filter, series filter? Because all are connected in series. So load current, line current, and current flowing through the series filter all are same, right? So this is same as IF. So what is VA rating?
VF into IF.
Correct. So can you just tell me what is the answer? 21.74 is IF and your voltage is 36.96. So what is the answer coming?
803.
Huh? What is the answer?
803.4.
Correct. 803.12. Okay. So now this problem is clear, right? The philosophy behind this problem. The voltage had harmonics, supply voltage had harmonics, and you don't want those harmonics to appear in the load bus or the PCC, point of common coupling. So you inject the appropriate opposite voltages to mitigate the harmonics of the supply side and make your load voltage sinusoidal. Simple. So accordingly you designed your filter rating, voltage rating, as well as current rating. Now see this second problem. Just read this problem. So now in this problem you have a series similar series active filter. So obviously you know what is the meaning of active filter. You have a inductor and then you have the DC bus capacitor of a inverter, voltage source converter, and this is used in series with the line, as I drew the single phase diagram also in the previous problem. And you have single phase AC supply of 220 volts. And what is the load now in this problem? Load is a diode bridge rectifier. But what is it used for? It is used for charging a battery. So you have a diode bridge rectifier, then you have obviously a battery which is of 264 volts, 12 amps. And obviously when you draw these kind of loads like this, you have some supply kind of thing. Now here in this problem, no source impedance is given, right? So this is sinusoidal. V supply is sinusoidal, and obviously this is also sinusoidal because there is no source impedance there. So ZS is not there, right, in this problem. And you feed it to a battery. Small resistance should be there. However, it is not told in the question. So this is 264 volts and this is 12 amps. Constant current, okay. Now tell me, if you had sinusoidal supply like this, feeding a battery based for charging a battery, what is the nature of your current, input current? Do anyone remember? So maybe this is the voltage amplitude, or this is 264 volts, okay. So 220 is RMS, okay. So what is the peak? 220 root 2. What is 220 root 2? 311 volts. Now you have 264 volts, E equal to 264 volts. This kind of battery. So only your diodes will conduct when? When your supply voltage or input voltage is more or less. Can anyone tell? When will the diodes in every cycle, positive and negative half cycles of the full sine wave, when will your diodes of the individual pairs responsible for conducting in the two cycles conduct? Let's consider for the positive cycle, when will it conduct? When the input supply voltage is more than the battery voltage. At this side you just see. Then only the diodes will be forward biased, right? So input current is discontinuous in normal scenario. But what is asked in this problem? You are using a series active filter between the lines to mitigate for the discontinuity in the current. Please understand this problem very carefully, right? Without the filter, you understand the scenario, right? Is it clear or not? Everything that I told is what? Without the filter. Up to this is clear or not? So I will write. Without filter, the battery charging current as well as the input AC current is discontinuous, right? Up to this is clear or not? Please tell me.
Yes, sir.
Achha, can you tell me how the input current will look like in this case? Without filter case?
Sinusoidal.
No. What is the input current? V minus E by R. There is an offset. E is sinusoidal. Small r you consider, okay? So that will not be sinusoidal, as you understand. Without the filter, I am telling you. Now what you are doing? You are incorporating a series active filter, which is sitting between the supply and the load. This full part is the load, right? Connected to the terminals of the AC mains. So you connected I can tell you just injected some this arrangement between the line and the load to reduce the effect of the harmonics. Harmonics were in the AC current. That is the input current. Clear? And also to maintain unity power factor. So what can you comment now about the nature of the input current after connecting the filter? How will be the input current? Because it is told in the problem to maintain unity power factor, also to reduce the harmonics. So unity power factor means the current will be continuous sinusoidal as well as unity power factor. That is no phase shift. So it is a purely sinusoidal current in phase with that of the voltage. That is what it is told in the problem after connecting the filter. So now can anyone tell me that if I make the input current sinusoidal, what will be the nature of voltage at this point?
After filter, sir?
Yes, this point.
If you have connected filter, then it will be the sinusoidal.
No, please understand the purpose. What is the purpose now? How you design the series active power filter? Please read the problem. To reduce the harmonics in the AC mains current, it is not telling you about voltage. Current was initially non-linear input current that you understood. Now after connecting the filter, you design the filter in such a way that you want your input voltage to be sinusoidal. Sorry, input current to be sinusoidal. Correct? That is given in the problem. And also to have unity power factor. Now, considering that the input current is sinusoidal, what will be the nature of voltage at this point? You made it sinusoidal, right? So what is the voltage at this point? I discussed this previous week also. Sinusoidal current, continuous current means that you are continuously injecting currents and the diodes are continuously conducting. In that case, if some voltage is there sitting here, this is fixed by the battery. So what is the AC side voltage? The diodes are continuously conducting. Please just imagine some switches. This is not switch because diode is uncontrolled device, okay? But still I am telling there is a DC voltage. Simple question I am asking you. If these switches are conducting in every cycle, what is the nature of voltage at this point? It is a square wave voltage, right? Getting my point?
Yes, sir.
This was DC, and the diodes are made to be continuously conducting by injecting sinusoidal current. So this point should by law of circuit theory, this point should obviously be a square wave voltage. And now if you calculate your filter to inject the difference between the two, difference between what? This voltage and this voltage. the square wave voltage, my sinusoidal voltage minus square wave voltage. If your filter can inject such voltages, then only my current can be sinusoidal, right? Input current. So that is what is the problem about that. For a continuously conducting sinusoidal current to actually appear in the line, for this kind of configuration, your voltage input to the load, which is actually a diode bridge rectifier based battery load, will be forced to be of square wave nature, and accordingly you just control your current or control or inject controllably, I can say, inject your voltage. This will actually be performing based on control algorithm that will decide to inject the difference between the two voltage. You will actually force its switching. You understand my point? This filter will not perform on its own. You have to control its operation by accordingly firing the thyristors, or it is a voltage source converter, so with IGBT based switches, you have to fire or give pulse to the IGBT switches in a controlled manner, and whose gate signals are generated by the control algorithm. And the control algorithm is working on the basic principle that the reference Vref of filter, if I assume, it is a voltage I can control of that the filter can inject, and I am controlling in such a manner that it is injecting difference between the two voltages. Because if I can inject such voltages, then only my current can be sinusoidal, which I actually want. So here the main focus is not to improve the load side voltage using a series active power filter. So we always don't use series active power filter only to improve the voltage quality at the load point. Also we use to improve the current quality at the supply point, because here improving the voltage quality at the load point is of no significance, because the battery voltage will inherently it is getting the current. We are charging the battery, so voltage at this point don't matter. You will not be penalized for a square wave voltage at this point, but you will be penalized if the current drawn is discontinuous and containing harmonics and offsets. So please understand the implication of the use of such applications or such components. So the application was here to ensure continuous charging of the battery, as well as continuous charging means continuous conduction of the diodes, as well as to ensure sinusoidal currents at the supply side. So that was the aim. So accordingly we control our device, that is series active power filter, to maintain such functionalities. So now you are asked RMS voltage at the input of the diode bridge rectifier. So this is easy, right? You can just answer it. What is the RMS voltage of such square wave voltage? Can anyone tell me? It is direct question. Once you know this, you know the answer. What is the RMS voltage at this input point? Input AC point, I can tell. Anyone? It is one line answer. Hello? You know that the voltage at this point is toggling between plus 264 and minus 264. Then you cannot tell the RMS value. What is the RMS value of such square wave signals? Anyone? What is the RMS? VRMS load, I can tell. AC. What is the answer? At these 2 points, input of the diode bridge rectifier. We're toggling between 264 and minus 264. So what is the RMS value? Yes, I want an answer. It is easy, right?
To 64 into root 2.
No, it is square wave voltage, not sinusoidal. So if a square wave voltage is having 264 and minus 264, toggling voltages and someone asks you what is the average voltage. What is the average voltage? Can anyone tell me? And what is the RMS?
Two root
No,
2
what
by
is the
pi
significance? No, don't remember anything. What is the significance of average? It is area under the curve. Average means area under curve. Mean of area under curve. Okay. So what is area under curve? Yes, it is 0, right? So average is 0 of such waveforms. But what is RMS? When you do RMS, you square, then you mean, then you average, and then you root. RMS means square, mean, then root. So when you square, this negative cycle will go on top, and then when you mean a continuously flat 264 waveform, then the amplitude is itself the RMS. So what is the RMS? It is 264 only. You square, then you mean over the full time length of a constant signal, which is 264, and when you mean it, it will come 264 only, square. And when you root, it will come 264. Because you squared, then mean, and then root. So what is the value, ultimate value? It is 264 only, right? So you should be able to just see the waveform and answer. You should know. You need not calculate or remember any formula. Formulas, you will get confused using formulas of different waveforms. If it is a quasi, then see the conduction period and then root over the conduction period by the overall time period. Then root it over. Okay. In a full cycle. Or if you assume half cycle, then there should be a symmetry between the negative half and positive half. Then only you can take one half of a cycle and then do however we do the calculations in the previous problems, like that. So you should know. Don't remember any formula, but you should be able to directly calculate the RMS, seeing the waveform. So RMS voltage rating of the active power filter. Can anyone tell me? Now you come to filter. So you know that the filter is sitting where? One side it is having Vs, another side it is having this kind of square voltage. So what should the filter inject? You apply KVL, right? Vs plus Vf equal to VL. Obviously in terms of phasors, because these are all AC signals. Because you know that load voltage or AC side load voltage, which is input to the DVR, is square. However, your supply, that is input to the APF, that is active power filter, is sinusoidal. Then what must be the voltage injected by the filter? That is asked. So that is the difference between the two. VL minus VS or VS minus VL, anything you do, because RMS value is asked. Okay. Don't worry about the sign. So can you tell me what is VL? Yes, hello. I want the RMS value. So it is just difference between the two. So what is VL and what is VS? VS is nothing but 220 root 2. You calculate for the peak. So peak is 220 root 2 sine theta, and difference of with 264, you whole square it, because when you square 264 will be flat. So that's why 264, and d theta and integration over a cycle, right? Half a cycle. Because over the other half cycle, one positive half and one negative half. Over the positive half, whatever is happening, negative half, similar thing is happening, because we are calculating RMS value. So 1 over pi, whole root over, right? So you calculate what is the answer coming. The limits are on theta, right? What is the answer coming? You calculate for 1, because in the exam also you need to do. So calculate and let me know the answer. You just break it down and then do the integration. Do the integration, I will wait, okay? You are doing with me, right? Hello? Hello? Yes, hello? Yes, hello? So we are doing for
Yes, sir.
one half of a cycle. In one half of a cycle, load voltage is 264 and current a voltage sinusoidal. So difference between two, then square it, then mean it, then root. That is the definition of RMS. Square, mean and root. Over one half cycle, why we are doing? Because the negative half cycle is just the symmetry, negative half symmetry of that. So one you do and then RMS it is, then it is symmetry. So calculate that, do this integration and then let me know the answer, okay? I will wait for you over 2 minutes and then you can just tell me the answer, right? Do with me because do one time. After that, I can tell you the answer because for the examination, you need this practice to break and then sine square you need to convert to cos and then you do. Okay, I will help you and then you try first. Okay, this integration is important. You try and let me know. Okay, I'm waiting. Yes. So anyone did the integration or you need some help? Because you will face this integration multiple times while solving the problems on series active power filter. That's why first time I just asked you to do, because you need to be acquainted and during the examination also you need to be fast. You need to know the steps. So you need some help or I will just tell you the answer. Hello? Someone tried some steps, then they can show me.
Slide is not visible.
Yes, no, slide is I will make you visible, but whatever I am telling is that you need some help while solving this. I can solve it for you.
Yes, sir.
Yes, sir. Okay. You tried something? So what I am telling, you do it, you break it, okay? Break this integration. So this is 220 root 2 whole square sine square theta plus 264 square. This is a constant term, okay? D theta. all are d theta. Okay, integration 0 to pi. Similarly, this is also integration 0 to pi. 1 by pi is there, and therefore you just do this third term. Okay, minus 2 into 264. You do with me. Okay, into 220 root 2 into sine theta into d theta. Similarly, this is also over 0 to pi, and everything is over root. Don't forget the root, because while calculating RMS, this is the main thing. You don't forget the root. Finally, you have to do the square root. So don't forget this step. So 3 terms are there. So tell me, what is integration of 0 to pi sine theta? What is integration of minus sine?
Integration of cos is minus sin.
Yes. Then what is the answer of this part, this term? Because this term is easy, right? You will only have a pi multiplied to it. Integration of d theta is theta, and pi minus 0 is pi. So 264 square into pi will come. This term is sorted. Now we solve this term. This term is relatively easy compared to this term. This term I will tell you how to solve. So you just know this formula, right? Cos 2 theta is 1 minus 2 sine square theta. This is, you are comfortable, I think, with this, right? Hello?
Yes, sir. Yes, sir.
Yes, then plug it in here. So what is sine square theta? It is 1 minus cos 2 theta by 2. Okay. You just replace sine square theta with this 1 minus cos 2 theta by 2. Then the integration will become easy. But first tell me, what is the integration of sine theta? Or tell me what is the integration of minus sine theta? It is cos, right? So what is integration of cos theta? What is integration of minus sine theta? It is cos, and then put the limits of pi to 0. So minus sine you integrate and got cos. Then put the limits. It will what it will come. Cos of pi is minus 1. It is coming minus 2, right? You understood what is done? Minus sign is cos, then put the limits. Hope you understand. Cos pi minus cos 0 is minus 2. So minus 2 times 264 times 220 root 2. This term is solved, right? And this term is minus 264 square. This was minus or plus? This was plus. Minus 2 was this term, okay, because this was minus. So what is it? 264 square into pi. Why? Because integration of d theta is theta. Pi minus 0 is pi. Solve this term and tell me. And everything you do under root. 1 by pi is for the whole, okay. And what is the integration of your this? So one term you will get 220 square into 2 into 1 by 2. 1 by 2 into pi. So pi by 2. And another term you will get 1 by 2 is there. So what is integration of cos theta? It is sine theta, right? So minus cos 2 theta is minus sine 2 theta by 2. By 2 was already there, so by 4. And when you put the limit pi to 0, what is it? 0, right? So this term goes away. Now calculate what it is coming. You take this term, I will highlight. You let me know what is coming. This term you do, then plus this term, then minus this term. divided by pi whole root over. Tell me the answer. I am also doing with you. Or pi you can cancel, okay, but this term will get, okay, so take and do. Final answer you tell me. Yes, this one is easy, right? It should not take much time. You please do with me. Please tell me what is the RMS value, okay? VF RMS. Don't forget the square root, okay? So what is the RMS value coming? Any one of you tell me. 1 by pi, remember you do at last. You first do these three terms. This plus this minus this. Then divide by pi, then whole root over. What is the answer? Tell me. I am getting 116. Anyone getting it with me? 0.2 I can say. So this is the RMS value of the filter, right? Everyone got the answer? Because we have 4 more problems left. We have to cover it. Shall I move on or wait? Done or shall I wait? Any doubt in this step? No one is answering. Hello? Hello?
Hello, sir. Hello, sir.
Yes, hello?
Sir, before I will get to 112. Suppose I will take the root 40, sir.
No, your voice is breaking. Can you please be loud? Hello?
Sir, before only I will have 112, sir.
No. After root only, I have calculated. After root only, it is 116.2. Just calculate once again. What you do, you do first this part, 220 square into pi, because 2 will get cancelled. After that, you add it with 264 square into pi. Then minus this third term, which I have highlighted with blue color. Hope it is visible in the screen. Once you are done with the 3 terms, you just divide it by pi. Then you will get some 13,000 something, and then when you root over, you will get 116.2. Okay.
Okay, sir. I will check, sir.
Check, it is coming 13,505 before the root. So after you take the root, obviously it is 116.2. So this is how you just typically do calculation for finding the RMS rating of the series active power filters, depending on the functionality you want to achieve, and we calculated by the difference of the 2 voltages, or the harmonic voltage has to handle like the first problem, or this kind of problems where you know the application is different. And after you determine know all the things, then you find the difference between the two to find out the voltage injected by the APF, and then you calculate the RMS value, right? So these are the steps that you should follow. So now coming to the next problem, you see, read this problem. So similarly, we have a series active power filter. What you know that it is a voltage source converter connected in series with the line, and you have the, now read the functionality in the problem. What functionality you want to achieve? Okay, you want to reduce the harmonics in the line, and also want to maintain, similar to the previous problem, you want to improve the current quality at the supply side. Your functionality that you want to achieve using this is this. And what is the application? Application is it is a RC filter, direct bridge rectifier with a capacitive filter of 2200 microfarad and resistive load of 20 ohms, just like the simulation we saw in the at the starting of the session. We saw the MATLAB simulation. Similarly, this is also a I can tell capacitor is little more, 2200 microfarad, and this is the DC bus voltage of load is decided to inject minimum voltage. So the problem is asking you now, your application is fixed that you have this single phase AC mains, no source impedance is given, you don't have to consider. Then you have this APF and then you have the load point. So now what you are having in the load, you are having a diode bridge rectifier, then correcting to RC load. So this was capacitor, okay, 2200 microfarad and this is 20 ohms. So this is the application. Now you want to have your DC bus voltage of the APF to be minimum to achieve this functionality. That is, your converter is switching, right? This APF. Now to inject some particular amplitude of voltage, you know, in the inverter also you might know, to maintain a particular line voltage at the AC side, your DC link voltage should be greater than a particular threshold, above a particular threshold. Otherwise your inverter will go in over modulation and you will not be able to achieve or build those particular voltages, reference voltages, as your reference voltages. So the basic point is your DC link voltage should cross, value of the DC link voltage should be above a particular threshold to make your application function actually, such that your APF actually serves the purpose. Your DC link voltage amplitude should be more than a particular threshold. Now through this problem it is asking you to find the minimum, that particular threshold of the DC link voltage. So first problem is the DC bus voltage, that it should in the volts of the load end and the RMS volt rating. So DC bus voltage you need to. So am I audible? Hello?
Yes, sir. Yes, sir.
So what DC bus voltage means at the load end. So your inverter voltage should also be above a particular threshold for the APF to function. But in this problem, what it is asking is to calculate this DC bus voltage. This. So don't confuse the DC bus voltage of the load. It is still okay. So it is the DC bus voltage of the load. For the inverter to operate, you can see by calculating what is the AC voltage, peak amplitude, and then you maintain it, the line, √2 times the line. We will discuss, we have already discussed that in the DStatCom also, that to build that particular amplitude of AC voltage for a 3-phase inverter, what is the minimum value VDC min. So if that is asked, what you will do? If this is VAC, phase voltage, so you do 2 times V phase peak, or √2 times V line to line is the minimum voltage, minimum VDC. Okay, same only. So why? Because inverter, these nodes are experiencing the line voltages. So what is the amplitude of the DC link voltage that should minimum be there to build such AC voltages? It is √2 times V line to line. That is the peak value of the how an inverter functions, that switches 2-level inverter. So that plus VDC, that will be the amplitude. And what is the AC side peak amplitude? Is √2 V line to line. So your VDC min should be greater than equal to √2 V line to line. But in the problem it is asking at the load bus, that is the load side, the DC side, this is the DC side, what should be the minimum DC bus voltage that should be injected. So this voltage V load DC min, this is asked. Similar to the previous problem, we knew what was the load side voltage, that 264 toggling between plus. At the DC side it was 264 maintained by the battery DC voltage. At the AC side it was toggling, that square wave voltage. Similarly in this also it will be like similar application. So the DC bus voltage or the load end minimum, if you know this, you know at this point. At this point, if you know the APF rating also. Similarly, after this, it is asked RMS voltage rating of the APF. So you know this, you also will be able to calculate this, just like the previous problem. But how to calculate this? Anyone? Once you know the DC side voltage, it is easy to calculate the APF rating by the difference V supply minus V load at the AC side whole square. Then you mean it and then you square root over to find out the RMS voltage rating of the active power filter. But how to calculate the DC voltage for this kind of load application. So I think it should be easy. Just think it is a single phase, I think single phase AC supply. Okay, so what to do? How to calculate DC bus voltage, load DC bus voltage, I can tell. That is the first part. Anyone, any idea? Hello? Yes, anyone? Hello? Am I audible? Hello? Yes, is my voice audible? Hello?
Yes, sir, your voice is audible.
Okay. Then you don't know actually the DC bus voltage, and you need to know the minimum DC bus voltage, right? So let us call it X, this DC side voltage. Now if you know that this is DC side voltage minimum X, then can you write what is the filter RMS component of the voltage? So V filter RMS, similarly 1 by pi integration 0 to pi 230 root 2, because that is the peak of the supply, sin theta d theta, sin theta minus x, because that is what we assume to be the minimum VDC of the load at the DC side of the load, d theta, and then you root it over. But you don't still know x. But what you recall, you need to know the minimum x. So how to calculate minimum? You need to know the minimum DC link voltage. That will also reduce the rating of the APF, right? So you integrate it and take a derivative with respect to x. And once you do dVF RMS dx, you will find the particular value of x. You put that particular value of x in this equation. Then you will get the value of VF RMS. Now, after you do this derivative, you will find a relation that x is equal to 2 root 2 by pi into V supply. Please remember, for minimum load point or load PCC DC link, DC bus, I can tell, voltage. So this relation will come. So you know x, you just plug the value 2 root 2 by pi. You can do this integration and then take the derivative of this overall term, and you just do df RMS dx equal to 0. You know, na, for finding the maxima or minima, you need to first find the critical point and then double derivative it, and if you find it positive, it is minima, and if you find double derivative to be negative, it is maxima. So we do the critical point, and you will find that x is equal to 2 root 2 by pi Vs, for which it will be minimum. Now you put that x and find VF RMS. First determine x, because this is the minimum DC link, DC load point voltage, which is into 230. What is the answer coming? Anyone calculate and tell me. What is the answer? It is easy, right? Please be interactive. Please solve with me. It is helpful for the both the assignments as well as for the exam. Hello?
207.
207. So this is what the minimum load side DC voltage using this concept. Okay. So now you know 207, you put this here back and you calculate the part B, which is the filter voltage rating. That is what it is asked, right? Just check RMS voltage rating of the APF. So that is like the previous problem. If you put x equal to 207 and do this integration, you will find the part B answer. So part B answer I will just give you because it is just like the previous. So it is coming out as 100 volts. Just check, okay? You just solve and you check, and if there is some problem, just let me know in the group, okay? So this is the type of problem. Now let us move to UPSCs. So now unified active power conditioner, the first problem will solve. Now this is nothing. This is a combination of series and shunt FPFs. The thing that I was telling you, you remember at the starting of the session, that actually to improve both the voltage and current qualities during load side distortion and supply side distortion, or due to the effect of source impedance, you need actually both. So these are UPSCs which incorporates both series and shunt APFs to mitigate the effect, the disturbances of both the loads and supplies, and ensure improved voltage quality at the load point and improved current quality at the supply side. Get my point, right? So always when I tell improved voltage quality, it is at the supply side. It is at the load side, sorry. Whenever I tell improved voltage quality, that means the supply was having some voltage distortion due to the effect of source impedance or due to the supply disturbances. So I want to improve the voltage quality at the load point always, and I want to improve the current quality where? At the supply point. You get my point? Such that we are not being penalized, because for our fault if we draw non-linear currents from the supply, we should not be penalized for that. That's why we make arrangements, shunt arrangements, to mitigate for those harmonic components. So current quality always we want to improve for the supply side. Voltage quality we always want to improve at the point of common coupling where the loads are connected for sensitive load operations, such that malfunction of the sensitive loads or motor based rotational loads does not happen. So you understand the point, right? Why we use those, both are required at those during those disturbances, right? Clear, or you have some problem? You should understand why you are using both, and behind that this problem is formulated behind that concept, based on that concept only, okay? So you read the problem. So this is a single phase voltage source converter, and it is generating square waveform, AC waveform, but square in nature, 220 volt RMS. That means 220 plus 220 minus, whose RMS is 220, and feeding a critical load of 220 volts, 4.4 kVA at 0.8 power factor. There is a load power factor. Now a single phase universal active power conditioner, UPSC, which consists of shunt and series APFs, just like the problems we solved previously, but in this problem you have both at the two VSCs with a common bus capacitor. Just like the UPQC, it is a UPSC, okay? It is designed for critical linear load. So the load is linear, and you are asked to find the RMS current rating of the shunt element and the volt ampere rating of the shunt element. So think how you can solve this. So now if you want to improve the supply side power factor for unity power factor operation, knowing that the load is linear load, what for you are connecting the shunt? Can anyone tell me? Knowing that the load is linear, don't have any harmonics, why you are then connecting the shunt? Anyone?
Improve the voltage quality.
Yes, hello. Why you are connecting the shunt branch? to provide reactive power compensation, right? Because the load is having some reactive components, 0.8 lagging power factor, right? To provide the reactive power through the shunt path, reactive current through the shunt path, such that the supply side is having unity power factor. For that we are using the shunt branch. Now RMS current, how you can calculate? You know that the supply voltage is like this, but you need to maintain actually sinusoidal current at the load point, load PCC, and your supply current should also be sinusoidal with unity power factor. That is, you have connected your supply like this. Please understand what is being asked. And you have this shunt and series filters. So this is the supply. After the supply, you don't have any source impedance. You have this series filter, this converter you have, then a DC link, then common DC link, another converter with shunt. Then you connect it, and then you have the load. Load is linear, so load currents are not an issue, but load has some reactive component which are compensated by this shunt arrangement, IQ, ILQ, like reactive loop. And this side, this is the load PCC. This side is the square. This side at the load PCC, we want sinusoidal voltage at this point, as well as sinusoidal current. For the loads to experience a sinusoidal current as well as sinusoidal voltage. So that's how the arrangement is. I think the picture is clear in your mind now. So in this situation, the RMS current rating of the UPSC to provide load compensation. Okay, load compensation means reactive power compensation. Whenever someone tells you load compensation for unity power factor, two things will come, either harmonic compensation or reactive compensation. But here harmonics of load currents are not there because it is a linear load. I hope you get the point. It is mentioned, right? It is a critical linear load. So only the thing is left is reactive power. Load is having some reactive power, that's why we want to compensate. So power, you know, PL 4.4 into 10 to the power 3 by 0.8 into 220, because this is single phase. Calculate what is it? Oh, it is kVA, right? So you calculate power. Power we are calculating, right? From kVA. So kVA multiplied by power factor is the power. So what is it, power? .4 into 1000 into 0.8, right? So how much power is the load consuming? 3520 watts. And what is the current? IL. It is just kVA by your SL by VL. So what is it? 4400 divided by 220. So what is it coming? 20 amps. So this is the AC load current. Now what is the active component of load current? ILA. I denote it by ILA. So it is 20 into cos of what? Or cos of theta is 0.8. So we know that 20 into 0.8, right? So it is 16 amps. Now you calculate fundamental of the voltage. Now also you calculate that reactive power of the load current you calculate. Active and reactive, okay. So what will the reactive component? 20 into 0.6, 12 amps. So my question is, load is having a reactive current component of 12 amps. Who will compensate for this 12 amps? Series or shunt?
Shunt.
Yes. So shunt, who is sitting there? That shunt APF. That will handle how much current? How much reactive current? 12 amps. Please understand, this is the overall system. And you have been asked the overall UPSC current VA rating and RMS rating of the overall UPS of the shunt element it is asking. Okay. Now, first we calculate reactive current handled by the shunt. Okay. Then we'll see if there is any active component or not. So reactive component handled by the shunt branch is 12 amps. That up to this much is clear. Why is it 12 amps handling 12 amps of reactive current? Because it needs to provide the reactive demand of the load, which is 12 amps. So it needs to provide that 12 amps to the load of reactive current such that your IS is not having any reactive component in it. So we understood that UPAC Q means reactive is 12 amps. Now I told you that active power transfer happens only due to the fundamental, because load is purely linear. So can you tell me active power transfer happens between fundamental of the voltage and current? Now here can anyone tell me what is the fundamental of the supply? Fundamental VS1 you calculate. Square voltage fundamental component.
2 root 2 by
Yes, but 2 root 2 by pi is of peak. So peak is what? This much. 220 volts. To calculate what is coming? How much it is coming?
190.
Yes, hello?
198.
198, right. So your, one second. Yes, 198 is the answer. 198, okay. 198 volts. So fundamental of your supply and fundamental of your load PCC. The difference between the two is the reason for which some active power is also consumed. Some active power needs to be injected by this. The difference active power needs to be injected, right? Because load is linear. The difference between your fundamental of supply and load will contribute to the some active power injected by the series. So can anyone tell this DC bus can be self-supported or not?
Yes, it is self-supported.
No, it cannot be, because it needs to feed some active power, inject some active power. Okay, it cannot be self-supported. Some active source needs to be sitting there. So it is never written. See, nowhere is it written self-supported DC bus. It has some source, battery or something sitting there to inject that active power. So what is the difference of active power? Because this side 198, this side 220, someone needs to be providing for that active power, because current is fundamentally linear. So 2 volts into that thing. Yes, you understand? Hello? 2 volts of that in phase voltage to the current needs to be injected by the series APF. And that reflection is appearing in the shunt APF. That by power balance. Whatever this pushes, this will take that active power, right? So can you tell me what is the active power? So let's compute the load current active component. Let us calculate. Load current active component is how much? Because we are calculating the current rating. So load current active component ILA is 16 amps. And source current, how much is the source current? 4400 into 0.8 divided by 220. It is 17.72 amps. So the difference active current needs to be pushed by the series appeal, and obviously the voltage difference I showed you. This is the voltage difference, 198 fundamental and 220. So the difference of the two voltage, that 220 minus 198 means 22 volts. 22 volts difference in phase voltage component and current component is like this, needs to be pushed by the shunt. So what is happening, we are doing a reflection, that 2 volts at the series side needs to be pushed to make the voltage same, and current that needs to be pushed, the different active power needs to be pushed. So whenever for shunt you are calculating, do in terms of currents, whenever for series you are calculating, do terms of voltages. But both the things needs to be balanced, because the processing is through the same DC link. Active processing, power processing is to the same common DC link. So now the difference in current, let us calculate, that will be pushed to the shunt branch, the active current. Okay, so active current of UPSC reflected at shunt branch is the difference between the two, right? 17.72 minus 16. So what is the answer? 1.772. This is the active. So I can term it as IUPAC active. So what is IUPAC net? It is the square of active and reactive components, Q or R, whatever you tell. So what is it coming? 1.772 whole square is the active, and reactive we calculated by based on the load reactive power that needs to be supplied through the shunt path. So what was it? Reactive was 12 amps. So we calculate, this is the answer, that the RMS shunt current rating. So how much is it coming? Hello? Yes, anyone doing with me?
Yes, sir.
12.13.
Yes, how much is the answer? Net current?
12.13.
12.13. Okay. And then this is the part A. Okay. RMS rating. Current rating I can tell. Now you calculate part B. Part B asks what? Volt ampere rating. So what is the shunt branch voltage? V shunt 220, right? So I shunt you calculated now. RMS. All RMS. What is RMS? 12.13. So now you calculate VA rating. 220 into 12.13. What is it coming? 2668.613 VA. So this is the answer. These two are the answer. So let's move on to the next problem. So I have two problems. I will just similar type of problems. I will just cover this problem. Other problem I will take up in the next session. Okay, because don't have much time. So do you want to do the two problems? I have two problems from hybrid filters. Do you want in this session or in the next session we can solve? Because I hope that you will be able to solve most of the problems. You will not face any issue. Yes, you will be able to solve, because this problem was more or less similar to the other problem. So I think there will be no issue solving the problem. Still you see this problem you just see. This problem you see. Other problem I will take up in the next session, okay? Don't worry. I'll take 5 more minutes, okay? So what is it told? A single phase voltage source inverter with quasi-square waveform, 220 volt 50 Hz is feeding a critical load, 4 kVA 0.8 power factor, just like the previous. But here it is told that universal active power conditioner using 2 VSC is used for design of critical load. Volt ampere rating is asked of the UPSC. And what is the functionality? Unity power factor at AC mains by shunt element and constant regulated sine wave. So can you tell, here also load is not having any harmonics, right? But the voltage, supply voltage is having harmonics. So similarly like the previous problem, you need to compute. So just calculate what is the, now quasi square, okay? So anyone remember what is the RMS? VRMS, what is it? Now VRMS is given. What is VDC?
VRMS is square root of 3.
V peak, I can tell. Now quasi waves look like this as I showed you. Now you know the RMS of this waveform, 220 volts, okay? You tell me this peak, V peak. So you know VRMS is what? This 30 degree, 60 degree is there. So 120 by 150, okay? Whole root into V peak, agreed? Then this is root over 2 by 3 V peak, VRMS. VRMS is 220. 220 by whole root over 2 by 3 is V peak. So calculate what is V peak is coming. Please calculate fast. 220 by root over 2 by 3. This is the supply side peak voltage because RMS voltage is given, and since we know the RMS value of the quasi square, we want to determine the peak value.
46.6.
26? 220 by whole root over 2 by 3.
46.6.
No. Just correctly calculate. What I am telling, 220 by whole root over 2 by 3. Whole root over, don't forget. You missed the whole root over. It is 269.44 volts. Now, what is VS1? Fundamental of supply. Remember quasi square, fundamental RMS. This is root 6 over pi. Sorry, just let me. We derived this multiple times. Why is it root 6 pi using power balance? Remember?
Yes.
Of a quasi square. Multiple times we derived it. Into V peak. Once you know V peak, from that you can determine fundamental. Because why always we want to find fundamental? Because VA rating we need. VA rating will come from two things, active and reactive. Active power transfer, I told you, only happens from the fundamental. That's why we are interested to calculate fundamental. So first thing you need to do, seeing this problem, calculate fundamental. What is fundamental? Root 6 by pi multiplied by peak. Peak voltage I told you 269.44. That is 210. Yes. 210 is the fundamental supply side voltage, AC voltage RMS value. Don't confuse. It is RMS value, not peak. What is asked in the problem? The volt ampere rating of the series element. Remember, that's why we are concerned with the voltages. So now you calculate. Now you understand, since this series UPSC we are concerned with the current, what will be the current handled by series element. Now UPSC has series and shunt. Now I ask you, what is the current that the series element is handling? Can anyone tell me? Because shunt is compensating for the reactive component of load current, the series element is handling only the active component of load current. So what is VF? VF is difference between fundamental of supply side and load side, as I already explained. Because supply side is distorted, square wave, quasi square wave, and load side is sinusoidal. You want to be sinusoidal. That's why you want to determine the rating of the series element, that how much voltage it should inject, RMS voltage, such that that happens. So the difference between the two it should inject. So easy, it should be easily calculated, that once you know that load side, what is the supply side fundamental is 269.44 and your load side is having 220 root 2 sin theta sinusoidal voltage, then the difference between the two for particular period, how much period? Between 30 degrees you don't have any 269.44 because it is quasi square, right? So minus 220 root 2 sin theta whole square d theta plus from pi by 6 to 5 pi by 6, that is 150 degree. You have this difference because it is quasi square, na, that supply side will disappear. Only that part wise I am doing the calculation. You square the waveforms, mean it, and then root. So how much duration this 269 will appear? So 269 you can do either minus that or that, because it is RMS, so it should not affect d theta, plus again pi by 6 to pi, it should be minus 220, because again that cycle came 30 degree cycle, total 60 degree, it is not having any, it is quasi square, it is no voltage is there. So if I do it and I mean over 1 by pi and I whole root over it, you will find the value to be 66 volts. You just see it, the calculate and see. So now I want the VA rating of the series element, because V, you do C by power balance, okay? V is fundamental into I fundamental active I fundamental component, okay? I will write this. Because it is unity power factor, so active and reactive don't have any meaning. All for unity power factor, full term is active only. Into 1 must be equal to load voltage fundamental or load voltage active power. What is load voltage active power? It is 4004 kVA, na? Yes. Into 0.85, it is the active power. So this is power balance. Now from here I calculate what is the current that is handled by the supply side. Now supply current fundamental IS1 also you can write, okay? So what is IS1? Equal to 4000 into 0.85 by. So using this you can just plug it in, 16.19 multiplied by 66 volts is the VA rating. So VA rating, if you want to calculate, it is just 66.05 into 16.19. It is coming around as 1069 volt amps. Okay, there is the answer. So I will stop here, and next week I will just discuss the one remaining problem, then we will move on to converters. Okay, so you can leave. Thank you.